Hello and welcome to Lab 5 for Physics 2212, Magnetic Molasses. Here's our table of contents. We're going to be going into some introduction, some fundamentals, some preliminary results of the rubric stuff. We're going to kind of describe the model and the experiment. We're going to go into the results for that actual experiment thing. We're going to go kind of similar method here. We're going to go to the glow script model and look at the results for that, kind of compare the two, see what's different, what's the same, and have some conclusion questions to kind of examine this here. So this whole experiment is based around the idea of Faraday's, Biot-Savart's, basic Newtonian principles, Ohm's law, etc. Largely more than anything else, it's about Lenz's law and how that negative in front of this interesting little guy right here is going to impact the direction of how a magnet falling through a conducting tube is going to slow down, which is really interesting. So other derivations will come up when necessary when talking about some of this stuff. So our preliminary results, just to give you a bit of a sneak peek here. We have our experimental time being 1.43 seconds and our computational time being 1.598 seconds. And here's our formulas: EMF equals the change in flux over change in time, or negative of that. This Lenz's whole thing. And then of course we have B, and that's magnetic flux, by the way. And this B, this is your Km 1 over R cubed, which is standard, and then this is your cross product, kind of interesting, different formula, but still same difference. This is our model. Just to emphasize things, this is about a magnetic dipole, so a pretty strong magnet we're using, a pretty ferrous one that is actually extremely strong. It's kind of hard to pull two of them apart with a dipole magnetic field. And the two we actually dropped in was the aluminum foil tube. We'll see in a second here. I kind of simulate Lenz's law to a pretty accurate degree. So here it is. This is not a video. This is just an accurate demonstration. But we took the magnet, we dropped it down here, and it took. You'd expect it to just go like that, but unfortunately, it kind of went like. And it fell a little slower, right? So that's very scientific noises there. You can kind of see a bit of a better demonstration here with this right here. So you see a dipole creating this current. And as you're falling down, it's inducing a current. This magnetic dipolar field is inducing a current on this conducting thing, which is really interesting. And the way that it's falling is actually going to, or the way that its poles oriented is actually going to induce a current in the opposite direction. But because of that, it's actually going to move. That induced current is going to create a magnetic field from that induced current to directly slow down the movement of the magnetic dipole, which I think is really interesting. So no matter which pole you drop it in, the south or north, it's going to slow down, which is really, really cool. So here's some checkpoint questions, just interesting things. Why can't we use a Ferris tube? Well, Ferris tube is something. Let's think about this for a second. If we drop a magnet which is attracted to iron down a tube made of iron, what will happen? It's going to stick to the side. It's not going to fall out. And how is it different than normal drop? It slows down, right? This current isn't induced in the air or in non-conducting materials, right? So it's a little different. But because this is a conducting material but also not magnetic, it's going to be able to create this induced current that will slow down, which is really interesting. Kind of help reinforce this, we have our glow script model. So it goes pretty complicated. Here's a bit of a better analysis of some of the more important parts. But you can see these segments explaining like this actual tube calculations, our dy, our length, grid step, delta, all these important things. And of course, the maths of the magnet, which is really important. You kind of have to assume some things with this because it kind of messes up scales when you put magnets on there. Some mu magnetism, some of these like constants that are pretty important. And once you get all those in mind, you can do like the mu hat, the bar mu, all these things, and eventually you'll end up getting a model that kind of demonstrates this idea, where your velocity goes down over time, and then it kind of like stagnates off a little bit. This really interesting like terminal field, which is a little less than like a terminal velocity of any other object would be, which is really interesting, and it's probably due to the induced current, right? And I mean, this computational model is perfect, so it's going to demonstrate a lot better than the actual representation one. So you can see this as it's dropping, this time it's going to take as it kind of decreases in the end, which is really interesting. Kind of follows this curve. If you kind of compare, kind of think about it for a little bit, why was the calculated model slower, right? Well, we can make a couple of assumptions based off like the error of the actual model. First of all, the magnet demonstration in this case very well could have been broken or busted or not nearly as powerful as we assumed it to be using our magnetic tracking things. So if that's the case, how are we to accurately describe its falling speed? Which is why it was probably a little quicker, because the magnet might have been old or dulled out or worn down, right? The discussion questions are as such. The resistivity of the resistor were reduced to as close as possible to zero. How did that dynamics change the falling magnetic change? Well, if it's resistant, the current will probably be a little bit stronger, meaning that the magnet, in theory, would technically be able to float in the middle of it, because its induced current would be equal to the dipolar strength, which is really interesting. But unfortunately, it's almost impossible to have something with zero resistance, so it's not really going to happen in a long scale thing. And in terms of holes or slots cut into the tube, this would affect it just because it would be inconsistent in the current traveling through it in a circular motion, so it actually just kind of tilt around and fall to the sides a little bit more, and it really wouldn't be slowed down a whole lot. Anyways, thank you so much for watching, and I hope you have a good day.